Hi, I am Rajdeep from IIFR Mumbai, and I will be telling you about a few athermal steady states in non-equilibrium dynamics of scalar fields. A steady is in quote, partly because there's been raging controversy over whether steady states are steady. In my cases, in most cases, you can figure out additional couplings, which will probably lead, there will be long time states. They will probably not be absolute steady states. There'll be steady states in some approximation, and that's why steady is in written in quotes. Okay, so just to, oh, okay, so let me start with my collaborators. Most of the work I'm going to present has been done by my student Mohammad Mursal in Islam, and he has graduated last year, and he's currently in Max Planck Institute in Dresden. And at least in the second part, we will have I'll talk about work which is done in collaboration with Krishnendu Sengupta of IACS. Okay, so here's a brief outline. I'll give you a few examples of athermal steady states and initial conditions, and very briefly tell you about how we study them, what kind of techniques. I will not go into details. If you are interested in the details, I am here. I can talk about it in all of the details. Then I'll look at two problems for you. The first one almost seems very simple and in some sense has been studied very, very long time back. It's a question of phonons coupled to fermionic baths. And it has been studied, for example, in general in the other way around, in the hot electron problem, where you think of fermions coupled to the phononic baths. Here we will reverse that. And I'll show you a couple of things. One is that there's lack of thermalization in one dimension in this problem. In low temperature, this is not surprising. I mean, we'll show that this just one dimension is too constrained. If you conserve energy and momentum, there's very little space for you to scatter. And that essentially allows us to understand why thermalization is not there in 1D or very, very slow thermalization in 1D, if you want to be exact about it. However, what we found is that when you go to very high temperatures where these constraints are relaxed, energy is no longer conserved, you don't need to worry about energy conservation. You still do not thermalize the long wavelength modes of the phonons coupled to a 1D fermionic bath. This actually came to us as a surprise because this argument would tell you that if you go to high temperature, this should all be okay. And what we found, some answers, we found that the bath is such that it basically creates dressed modes of the phonons, and these dressed modes of the phonons remain undamped, and that's what leads to absence of thermalization in one dimension, even at very high temperatures. So this is one sort of thing that I'll tell you about. Then I'll shift gears and talk about interacting scalar fields, but this time they have some conserved dipole moment. So they have a dipole symmetry. And in this case, these models have been recently very useful because they're a starting point in thinking about things like fractons and so on and so forth. You have to gauge these models and then think about them in terms of fractals. But the ones that we are going to deal with are the ones with a global dipole symmetry and no gauge fields. In this case, we will see something interesting that we can do the thermal phase diagram and we get certain states in this. But when we do quench dynamics or ramp dynamics and look for steady states, the steady states show us phases or states which has different symmetry from the ones that you get in thermal equilibrium. So it's not a simple way of understanding, you just go from this equilibrium phase to that equilibrium phase. You get altogether new phases which are seen only in the non-equilibrium dynamics, and they do not occur in the thermal phase diagram of the system. Okay, so let's get started. At thermal steady states, what are we going to talk about? Here are a few examples. This is data from Lavouille and others. And what they were doing is they had a bunch of Bose-Einstein condensate, and they had a central Bose-Einstein condensate well, where there was a beam which was giving rise to dissipation or loss of particles. And these coupling between the wells, which is like a hopping between the wells. So this effectively mapped onto some effective model of a driven dissipative Josephson junction. This is the dissipation, the hopping constitutes the effective driving, and so on and so forth. Now, what they did is they basically looked at the density of the central site after time evolving, and they looked at this as a function of the dissipation. Okay, so the blue lines are when you start the initial central well with a fraction which is equivalent to everything else. It's filled up. And the red lines are when you start with an almost empty central site. Okay, and what you see is that for a parameter range of gamma, somewhere here, the final steady state depends on the initial condition. So this is clearly an Athermal state because it doesn't go to, it basically goes to different states depending on where you start with. So it remembers how much, where you started with. The second, of course, is MBL, lots of controversies. Again, I want to stay away, so the study is in quotes. So, but this is true that if you do experiments on this, what you do is you take strongly disordered systems, and then you start them with a 1, 0, 1, 0, 1, 0 pattern of density. And then you look at the imbalance between the odd and even sites, the ones where you started with 1 and the ones where you started with 0. And you see that if you have 0 disorder, it very quickly goes to 0 because, in absence of the initial condition, there's nothing that the system can distinguish between the odd and even sites. However, if you do it at a finite disorder strength, and as you crank up the disorder strength for a long time, it seems like this is going to a finite value. And the only thing that can distinguish between the odd and even states is the initial condition. So this is often cited as an example that the system retains long-term memory of its initial condition. And again, lots of debate whether this will be remaining here or will just go slowly to 0. Without going into that for long enough times, you do see that the system has gone into a state which remembers the initial conditions. The third example is, I guess, we'll probably see a lot about this in the conference, is quantum scars. Again, for some very specific initial conditions in these systems where you have to start with some 1, 0, 1, 0 pattern or something like that, the system seems to remember initial conditions for very, very long times. If you start with some other state, it does not. So this is something very specific to a specific set of initial conditions where you can initialize the state. Now, to give you this idea that people have seen in various contexts Athermal steady states or long states which extend for a very long time, which are definitely not thermal equilibrium states. And this allows us to ask, how do we study this kind of non-equilibrium dynamics and the steady state? Our choice of technique is a Keldysh field theory or a non-equilibrium field theory. You can basically take the time evolution of a density matrix, convert it into a path integral, and you get into a path integral with 2 different contours, one for the forward and one for the reverse. And so you have doubled fields at each space-time point, phi plus and phi minus. I'll not go into the details. And then you can basically work out the whole set of Keldysh field theory and get various non-equilibrium correlation functions out of this. Now, this is traditionally used to describe steady states, for example, IV characteristics of devices, or dynamics with thermal initial states, for example, hot electron problems. But this kind of field theoretic techniques are traditionally not used to describe systems which are starting from very non-equilibrium initial states. And where specifically where initial conditions play a very important role. And one of the things that we figured out what was happening was that the textbook Keldysh field theory requires a thermal initial density matrix to work. In a series of work with my earlier student Ahana Chakrabarti and now with Mursalin, we have extended this to basically give you a field theory which can deal with dynamics of these things, which are starting from arbitrary initial conditions. You give us a density matrix, we know how to do this. I will not go on into details of this, but if you are interested, I can talk about it. The end result is we can write down dynamical equations for correlation functions with the usual structure of self energies, vertex functions, etc., etc. Okay, so with that basic introduction, let's now jump onto the first problem, which is absence of thermalization in phonons coupled to fermionic bath in one dimension. So what are we looking at? We're looking at a very simple model. Phonons are just given by standard field with omega k being the dispersion of the phonon. We'll put it on a lattice. So in 1D, omega k is omega naught sine ka over 2. So omega naught is like the bandwidth, but it also contains the phonon speed. If you go to the weak coupling small k limit, you'll get the phonon speed out of the omega naught. The fermionic bath is again very simple. It's a 1D bath, which is fermions hopping on a 1D lattice, which gives you a dispersion of epsilon b cosine ka. Okay, and then we turn on a system bath coupling where there is a Scheidegger k psi k coupled to the phonon field. This is, of course, the standard form factor of the deformation potential, so that as q goes to 0, the coupling actually goes to 0, and kappa is the strength of the electron phonon coupling. Okay, so that's the setting. We will deal with the reverse thing, that the electron will be treated as a bath, unlike in T's case where the baths were being evolved. The bath will be assumed to all the bath distribution functions. Bath is large. So the bath distribution function will essentially be characterized by a temperature and a chemical potential. Okay, and so this is a simple setting that we will like to study. Now, as you can see from here, the phonon actually couples to a particle hole excitation because it's Scheidegger psi. So it basically couples to a particle hole excitation of the fermionic bath. And if you write down the bath spectral function, the thing that comes up is the density of states of the particle hole pairs. This is going to, for example, control the dissipation and the noise in your system as you go through the system. Yeah. Tight binding chain. Yes. Yes, exactly. Okay. Everywhere. Yeah. So every side. No, every phi of x is coupled to a bath. Yeah, not an end-to-end coupling. Okay. So what do we want to? Yeah. So since we want to study non-equilibrium dynamics, we came up with this crooked theorist way of putting an initial condition. We just said I'm on a lattice. I have odd and even momenta. And odd and even momenta, I'll put 1 and 0, kind of getting it from the other case. And so this is the nk of 0, what it looks like. This is what it will look like if I turn on a temperature, and so on and so forth. So that's what my initial condition looks like. And I'm interested in asking, I calculated the phi-phi correlator at large times, which is related to 1 plus 2 times nk of t over omega k. And I ask, okay, does it go to its equilibrium value with the temperature of the electron bath? So here is the dynamics of the correlation function. This is at low temperature. So what you see is that when k is 0.1 pi over a, this is what the dynamical correlator is doing. This is the thermal value. Whereas when you go to large k equal to 0.4, it basically goes to its thermal value. There's a lot of oscillation. There's no thermalization and so on. And you can figure out the deviation of the long time. You can just take an average value here and then look at the deviation of this from the thermal value. And you will see that this is 0 up to a point, and at some point it starts growing. Okay, this is at low temperature, long wavelength modes fail to thermalize. This is easy to understand. if you look at the particle hole density of states, open up a 1D particle hole density of states of a Fermi gas, it has this lower limit and the upper limit, so the density of states is finite only here. And what is happening is your phonon is basically cutting through it like this. So if you have a low k here, the phonon effectively does not see any path. This is what we said by saying, if you were here, these two things are almost going as Vf of q. Omega is going as Cs of k. Unless Cs is equal to Vf, you're not going to match energy momentum constraints. So this is understood that you just don't see a path. Fine. It's 1D, it's constrained. And if you calculate carefully higher order terms using diagrams and so on, you can show that the first terms which will finally lead to a dissipation will be of the order of kappa to the power 8 in this case. But let's not go there. What's more interesting is now, I have gotten up to 0.2 epsilon B. Epsilon B is the bandwidth of the bath. So this is pretty high temperature. Yeah? And I'm again calculating the deviation of the dynamical correlator from the thermal value. And you can see that at low K, it again starts picking up. So the low K modes again fail to thermalize. Now you have a problem because at this point, if I look at the particle hole density of states, they are all over the place. The phonon should see a bath, and there's no particular reason for it not to thermalize. What happened? So we were wondering what happened, and then we tried to look at the phonon spectral functions. And lo and behold, this is the phonon spectral functions for different values of K. What you see is the initial dispersing thing, which has been broadened by the thermal factor. But then you see this very sharp feature in the Dresden phonon spectral function, which is farther away from the original phonon peak. And if you look at it, you plot these points, you will see that these points are just above the particle hole band edge. So if you had a mode there, of course, it will not see again any bath, but this is not a phonon mode. This is a mode that you have formed because the phonon is getting dressed by the bath. So what is happening here? What is happening is that the bath spectral function in 1D has a divergence, has a 1 over root omega divergence at the gap edge, at the band edge, okay? And if you have a diverging bath spectral function, what you can show is that the similar kind of divergences will occur in the self energies of the phonon. Now, if the self energies are diverging just outside, what you will see is that the Green's function will have to go through a zero just outside. And so it will basically create an extra mode, and this mode is the undamped mode. Now, normally this is seen in, for example, things like polariton, but then you are just talking about mode coupling. Here, remember, the bath is some incoherent thing, and it's like the sharp divergence in the density of states. That is what is enough, although it's not a single mode, to give you this extra mode outside, okay? For example, if we go to 2D, there is a weaker divergence, logarithmic divergence, and this will not happen, and it will get washed out. Okay, so the idea here was that the polariton modes do not see a bath and hence do not thermalize. So this is one of the new things that we had found, that the bath can dress the phonons, create these modes, but create these modes which are outside the range of the bath that you are going to see. Okay, and then you can look at various features of these carefully and so on. For example, the spectral weight decreases with Vf minus Cs. So the best way to see this would be when your Cs is close enough to Vf. I mean, if the phonon and the gap age are widely different, the spectral weight will go down in this mode, and because the mixing will be small. And that basically would make it clearer that you want to be close to the gap edge, you want to have a large system bus coupling, etc., etc. Okay, so that's the first setup story. And yeah. No, in some sense, yes, because the divergence of the density of states if you go into real time, for example, the similar kind of divergence in self-energies will give you memory kernels when you Fourier transform them. And these divergences will give you power laws in the Fourier transform. I don't think you will see this without a single pole. It's not a mode coupling thing here. Yeah. So, okay, the next one is the quench dynamics of bosons with dipole symmetry. And this is work done with Moessner and Dibyendu, which recently came out. We are interested in looking at fields which have both a charge conservation and a dipole moment conservation. Why? Because if you go and take these global, quote unquote, global symmetries and then gauge them and do a few more things, you might end up in things which are like Frackton phases. These are phases which host elementary excitations which have restricted mobility. They can move in one direction, let's say, without creating additional excitations, but in other directions, they have to create a lot of excitations to move. These theories usually show very strong UV-IR mixing, so ground state properties are often dependent on exactly how you regularize the theory. And these are often also have large ground state degeneracy. There's a huge history of people working on this, and it has again come up recently more interesting. One experiment which was done was on tilt-test Bose-Fermi-Hubbard models. And in this case, what you have is you actually have a kinetic constraint, so that when things are shifted up, the only thing you can do is you can hop two of the things together. You cannot hop a single particle. And this has led to a whole new slew of works on things like Hilbert space fragmentation, non-ergodic dynamics, etc., etc. Here are some references, not exhaustive. But we are going to study something much simpler. So our question is that, okay, let's take a scalar fields with dipole conservation. Okay, so we want to write down a field which has a U1, which is a conserved charge, and it's also symmetric under e to the power I d dot x, because that will give you a conserved dipole moment. Okay, this was written down by Pretko in 2018. Simple theory for that. You just have a scalar field theory like term. You have a phi-4 term. And the important thing here is there's no spatial gradient, so no kinetic energy, no single particle kinetic energy in this. And then the interactions have gradient terms. So, these are the all things that lead to correlated kinetic energies, etc., etc. Okay, so there's no gradient term to start with, so it will in general lead you to a strongly coupled theory. And so we are not going to gauge any of this. We are still going to look at this global symmetry. And similar models where instead of del T square, people had done with I del T was done by Jensen and Raz and others. Okay, so how do we solve it? We go to a large n flavor, we just increase the number of bosons, basically, and then work with a coupling which is scaled by 1 over n. You can just Fourier transform all of this. You will see that you will get a K1, K2, K3, K4, which is a complicated function of K. You work in the large n limit, so you can take saddle points and mean field theories. So this is how you basically can write down a saddle point by just choosing GK to be phi star K phi K. Oops, what did I do? Where is the zoom? Oh, just make it full screen. Right, sorry. Okay, good. Okay, so now a couple of more details here is that these things do depend a lot on how you regularize. So in our case, we just regularize it on a cubic lattice. So whatever I'm going to say is basically on that. Then you can just do a mean field theory. So when you do a mean field theory, you come up with these terms. There's a m square, which is an effective mass or gap in the system. There's a kappa, which gives you the effective bandwidth. Okay, and this will give you the gap and the curvature. So for example, if you have a finite kappa, that will break the dipole symmetry. If your system throws up a finite kappa, you break dipole symmetry. You can also look for whether the system condenses, which is just simply the usual condensate density. And we have, at least in equilibrium, the usual thing that the system is, if it's condensed, it's gapless. If it's gapped, there's no condensate. Okay, so these are the equations that you need to follow. Now, what are the possible phases? You can have gapped phases so that you are not condensed. And then you can have two possible cases. Either kappa is 0, where dipole symmetry is conserved, or kappa is non-zero, dipole symmetry is not conserved. In the gapless case, you will see that kappa equal to 0 is not an option because your Goldstone modes will immediately give you dispersion. So these are the three possible states you can get. Okay, a condensed phase with dipole symmetry broken, a gapped phase with dipole symmetry conserved, a gapped phase with dipole symmetry broken. Okay, there's some saddle points and mean field theories you can do. Here is what you get for solutions of the normal phase case. You see that there are multiple solutions already. That indicates to you that you are likely to get into a first order transition. This is m square and kappa for the normal phase. And again, sigma square and kappa for the condensed phase. You can see that there are multiple solutions to these equations. So what you do is you basically calculate the free energy and look for a minimum. And that gives you finally these phase parameters. So what you see here is that you have a gapped phase with kappa equal to 0, or you have a condensed phase, and you have a first order phase transition between them. You do not have a gapped phase with the dipole symmetry that is broken. Okay? So this is the first order phase transition. You just go from a normal phase with no dispersion to a condensed phase where kappa and sigma square are both finite. You can go up in finite temperature. This is still works through. Okay. What we wanted to study in the last maybe 5 minutes, let me tell you about, is the quench dynamics. So what we were doing is we were quenching the bare mass of the theory from an initial state to a final state. Okay, and then we use our dynamical equations with this initial condition. And what we ended up getting is an equation for the Green's function in terms of something which we can call the omega square k comma t. If you just froze it at that snapshot and constructed some Bogoliubov quasiparticles, this would be the dispersion of those Bogoliubov quasiparticles, for example. You can write down equations, not so important. What we have done is, so basically what you have is, you have equations for m square in terms of g, okay, gk, which is a Keldysh correlator. M square feeds into gr, but m square kappa and sigma. So you need to close the final equation, which is you need to write gk in terms of gr. And this is where our dynamical equations of using Keldysh field theory for arbitrary initial conditions come in. In the end, you have a closed set of equations which you can solve for any time. So here is the results. If you have an initial state, we are starting deep in the condensed phase, minus 18, and we are quenching immediately to m naught square f minus 11.5. You see kappa is finite, sigma square is finite, m square is 0. Okay, so we are again in the condensed phase in the steady state. You can just look at these values of kappa, sigma, and m square, and that's what you will get. If you go to m square final of minus 10.5, then you get this value that sigma square has gone to 0, okay, which is basically means you are no longer condensed. As a result, the mass gap has come up, fine, but you see that you have a very large kappa. So basically in sort of a steady state, where the dipole symmetry is broken, okay? And if you go even farther to minus 9.5, what you see is that again, sigma square has gone to 0. Now m square is large, but highly oscillatory. Kappa is very low, and at least the bottom of kappa touches 0, but it seems to be oscillating around this value. And so you get into these three different regimes based on where you are going in the final steady state. And so you can put it in a phase diagram in terms of the quenched final mass. So here is where you are basically in the just in the condensed phase, sigma square vanishes. In between, you get this, UN conserved, but the dipole symmetry broken phase, which you never saw in the thermal phase diagram. So that's the interesting thing where you can see that this extra phase can come from dipole symmetry broken state, which comes only in the steady state, but doesn't occur in the thermal equilibrium at all. Okay, now once again you can ask, is it a pure steady state? And the answer is unlikely, because this is a large n calculation. Okay, if you start taking into account 1 over n square, etc., you will add some dissipative terms into this only has dephasing dynamics in large n, because it's, mean field, but time dependent mean field. You will add dissipation into your problem, and most likely things will slowly go away from this to some thermal phase. Okay, let me not go into the ramp dynamics, but maybe just one point that till now we were doing instantaneous quench. We can ask if we do it with a ramp time scale and change the ramp time, and basically tau tends to infinity is an adiabatic ramp. What we find is, as a function of tau, this intermediate phase exists only up to a particular tau. Beyond that, you go back to your thermal thing, where you just go from a condensed phase directly into the symmetry conserved phase. So this is something that is truly non-equilibrium. If you go to large tau adiabatic limit, you don't see this. Maybe I can skip the quench dynamics from normal phase. There are some oscillations at very long time scales you saw here. And for example, suddenly the oscillations become very, very large. We now understand this. What is happening is kappa controls the bandwidth. So when you are oscillating with different Ks, different dispersions, basically you are integrating and you are dephasing all of this. Now, when kappa becomes very small, suddenly at this point, you see there's a huge drop in kappa. You will see that the dephasing vanishes. And as a result, the oscillations start increasing. This is simply because you have a very small effective bandwidth in your final thing. So maybe I can stop at this point. So again, this is the summary. We talked about a couple of athermal steady states in non-equilibrium dynamics of scalar bosons. The first one was that phonons coupled to fermionic baths do not thermalize even at high temperature. That's the interesting part. And this comes from some Dresden polarinon modes. The second part is the fact that if you have interacting scalar fields with dipole symmetry, in equilibrium, you just have a first order transition where both the symmetries are broken. But if you do steady states after quench, there's a new phase with a broken dipole, but conserved U1 symmetry. I'll stop here, and if there are questions, I can take.
Okay, time for questions. Yeah,
I had a question regarding the first part of your talk. So the essential point in getting this a thermal steady states is presence of divergence in the bath spectrum, or is there an energy scale for that as well? Or
no, so in the phonon case, you're talking.
Yeah.
Yeah, so no, the divergence, so here is probably the, yeah. See, what happens is, as a result of divergence, so the bath spectral function is roughly the imaginary part of your self-energy. Okay, so your imaginary part of self-energy will pick up this divergence from the inside. Of course, from the outside, it's zero because there's no bath. If you take this and do a Kramer's chronic, you can look at the real part of the self-energy. And the real part of the self-energy actually picks up a divergence. This is the real part of the self-energy basically picking up a divergence. Now think about it, you have a omega square minus omega k square minus something which is trying to diverge. It would have to go through a zero, right? So it'll drive it to zero. So the divergence ensures that you must have a pole outside the bandwidth. So that's what it ensures. So once there's a divergence, you don't. How far? depends on all the details.
Thank you.
Arnab, you are. This related to the second part of your talk. So there was this steady state phase which didn't have any thermal analog, right? Which was presumably an artifact of this n tending to infinity limit. Is there any, do you have any idea how to estimate in 1 by n how long this pre-thermal window might be?
Yeah, so that's a good question. So here, it's a little, because what will happen is that, the m's, it'll depend on how, I mean, for example, suppose I expand around this saddle point and look at the fluctuations around this. Those things, will start depending on, you're basically expanding around a time-dependent point, right? So those things will depend on m square, etc., etc. Now, your question is, should I first feedback all of these and find a new m square, or do you want me to look at this m square, assume it's kind of stable, do it around that, right? If it's around this m square, then I can go to next order, because this only involves Bogoliubov quasi-particles which are non-interacting, right? So if you go to the next order in 1 over n, those corrections, I believe, will come with some lambda 1 over n times lambda 4 square, effective lambda 4 square over mass of T. That's roughly the answer. But then that will now ask whether m square of T will change dramatically or not. It's a, I don't know a simple answer in a non-equilibrium setting unless I do the calculation. Yeah, it's hard, but
You're welcome to try.
So, Rajdeep, so if you connected a fermionic system to a fermionic path, and if the path bandwidth is broad enough, then of course the would thermalize, right?
Yeah.
Even though it still has a diverging, so maybe the divergence is not that crucial.
No. So, are you talking about a fermionic path which has bandwidth? So here, for example, remember that I am dealing with a lattice path. So here, for example, if I had an infinite thing, right? What I will see is that this divergence, which is a band edge divergence, right? This is a divergence at the band edge. So that band edge divergence will go away. You're saying just make it very large.
No, I'm saying if instead of a phononic system coupled to a fermionic path, I coupled a fermionic system to a fermionic, then of course I know it would thermalize.
Yeah, but you will get power laws all the way. So you will have to, if you put it with a finite bandwidth, you will get this 1 over root omega will give you some 1 over t to the power 3 halves or something like that, right? So any correlator will go to its value, but with a 1 over t to the power 3 halves deviations, for example.
Yeah, it might be a power law like relaxation, but it will always thermalize. I'm saying there's no, but here you seem to not get relaxation to steady state, right? That's what.
Yeah, so in that case, here we are not getting it because, so here what is important is the particle hole density of states, because the phonons are actually not coupling to independent fermions.
Right, yeah.
Right?
So it's because of this polarons somehow.
So it's the polarons, etc. But suppose I give you a fermion just coupled to a fermionic path, and this path is much, much bigger. Then again, the question is, how long and what deviation are you interested in? It'll go to its value, but it will not, basically it can't. So for example, even here, if I make the path very, 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 very large, right, you will see it somewhere, but the spectral weight in that will go to 0 in the new modes that I'm talking about. So here. Just give me 1 second. So this weight, if you make the bath band very, very large compared to the phonon somewhere, okay, this weight will go down on you. And in the limit, this weight will go to 0. That you can show. So that's how, in this case, even you will, if I make the fermionic path infinite or very large bandwidth, right? What will happen is the weight in these modes will go down, become tiny. It will be finite, but tiny. And in that limit of this hitting infinity, it will go to 0. So that's how you will reconcile. Yeah, so here was the answer, I guess. Spectral weight increases with the system. System path coupling is the electron phonon coupling here. Yeah. So the weight here will increase. Yeah. In fact, in that way, it will be better because the weight here will increase. And this mode will basically, so larger system path coupling you have, see, this is ultimately formed by dressing. So if the larger system path coupling you can give me, I'll get more weight here.
I would naively just imagine that maybe treating the fermions not as a bath, but as another system and analyzing like collective modes of them. Why not that point of view for this new mode?
No, so what I did was I always kept the distribution. So while calculating the bath spectral function, I just kept the fermion distribution function for free fermions, right? Which means at any time I'm assuming that it's the same bath. But you can do that calculation. You are asking me, can I put, fermions, phonons talking to each other, self-consistently solve it? We try. There's a project going on where we are trying this. Turns out it's not so simple. There are all sorts of instabilities that happen, and you have to be very careful how accurately you are solving this differential equation. So that's what we want to do. But till now, we have run into instabilities where things go off in directions where we know it doesn't make sense. Or maybe there are real, I don't think they're real instabilities. I think they're just because of how coarsely we were solving the differential equations. There are those issues, but we would like to do them.